of electricity. So, followed by copper, followed by, followed by gold, followed by aluminum. Right. And then, what's a circuit? An electrical circuit.
Complete path for
Current.
a complete
I'm
path
glad you
for-
didn't say electricity.
Yeah, I can't remember. I wrote it all down.
Yeah, it's the flow of electrons, right? Which is current. Current.
Oh, what-
Electrons.
oh, what is current versus electron?
Well, you have to envision, the analogy I use is I've got glasses up here.
Complete path for current flow consists of voltage.
They don't consist of voltage.
Consists of voltage.
Well, you got to have three things before you have a current flow,
Well, I
right?
gotta finish.
What's the three things you have to have before you have current flow? You have to have a source, right? Voltage source. You have to have the path, right? And then, of course, we need some type of load, right?
It was on the other side of my path.
Okay, there you go. The analogy I use is I've got glasses up here, and we all start off empty, and then I'll start pouring them in, and I fill one glass up, and I take it and fill the other, fill the other, and fill the other. Well, what we got is we got empty glasses moving from this side to that side, and we got the glasses that I'm filling move from that side to that side. So every time you bump an electron out and move, it leaves what we call a hole that's refilled. So we have positive charges moving from positive to negative. We have negative charges moving from negative to positive. So that's why different people teach different current flows. So originally they thought current flowed from positive to negative. But then they realized it was what? It was electrons that was actually flowing, right? You understand? And then the negative pushes them and the positive attracts them. So if you ever talk about conventional current, they're teaching what we call hole flow, the flow of the positive charges moving. Okay. And that's called conventional current. So there's two techniques. The military teaches in most community colleges teach electron flow, but you get into a lot of engineering programs and they teach hole flow because it just. And what's so strange is when we came up with different devices. Y'all know what a check valve is? In fluid power? Yeah, it only lets the fluid flow in one direction. Well, we have a symbol, a check valve in fluid power has this symbol right here. So that's the symbol in fluid power for a check valve. Oh, I'm sorry. I can see it. I can see it fine.
So basically, conventional
Is the original thought of current flow because they thought positive had the highest potential, and they assign and who's positive and who's negative. You know, they assign those symbols. You know that.
But the current one that you teach is.
We teach what we call electron flow. Yeah.
Well, you told me that.
Yeah. So this is it up there yet? So this is the symbol for a fluid power check valve. So if the fluid tries to flow that way, it seats the ball and it can't get through, right? If the fluid comes there and flows that way, it unseats the ball and allows it to flow. So this is the symbol for a check valve. In electronics, we call this a diode. And this only lets current flow in one direction. But this is electrical current. Which way do you think it flows? Huh? It flows this direction right here against the arrow. And that's electron flow. So it flows against the arrow. So the problem is when they first came out with these symbols, they were using conventional current flow. But when they came up with electrons, so every symbol that we have in electronics that has an arrow on it, it's going to flow against the wall, against the arrow. Yeah. So these are current valves. We call them transistors. I don't even know this, by the way. But this is the control lead. So every valve has a control, right? You understand? But the actual control is this direction right here. So that's the way electrons flow. It flows a lot against the arrow.
Against the what?
Against the arrow.
Oh, arrow.
Yeah. This guy right here. And we call this an NPN transistor and we say not pointing in, the arrow is pointing away from the center. So if you ever heard NPN, that's what that stands for. And then we have another one, symbol that looks like this. That's called a PNP. Pointing in, and the current on this one, electrons would flow that direction up there through the main valve. So y'all understand, most people understand how valves work, where we get a mechanical advantage off of it. So if you ever tried to get your sink running wide open and stick your hand up there and stop the flow, you can't stop it, right? You understand? You'll end up squirting water all over the place. But you can take that valve and turn it very easily, right? Because you get a mechanical advantage with the valve. So that's what transistors do. So we take a real small current coming into this guy right here, and it controls a lot of current between the other two leads. So these are current valves. And we can use them to do all kinds of things with these. So when you say which way does current flow, well, here we're going to say it flows from negative to positive because we teach electron flow. But you might read a book and it says it's flowing the other way, but they're talking about what? Conventional current. And guys, as far as your math goes, as far as your laws goes, all your Ohm's law and your Kirchhoff's law, it makes no difference. The polarity on the resistors makes no difference. The only thing that I know of that makes the difference is the law of magnetism. Because which direction the current flow depends on what we use. So one, we might say, okay, it's the right-hand rule for electron flow, and it would be the left-hand rule for conventional current flow to figure out which way the North Pole is, if you ever had to do that. Sometimes we show that, but you don't actually need to know that. So you can figure out which direction a DC motor can rotate using what they call the right-hand rule or the left-hand rule. And I'd have to go by and look them up, right? But might be the right-hand rule for electron flow and the left-hand rule to figure out which way the motor will run. So all we know is it makes charged particles flow, right? Of course, like I say, we teach electron flow. That's the way I learned it in the military. Now, a common circuit is going to have some type of control device, right? Of course, this is a real good example. Here we're using just the standard switch, the turn, and y'all use this control device all the time.
That's potential flow?
No, this is electron flow, because notice they're showing the particles moving from negative and going in this direction toward positive. Well, no, the positive is going to be where you want it to be.
Oh, okay. Clarify.
Yeah.
Clarify. In your diagram, always the little short line is the
negative,
and the long line is always positive.
Right, if you draw the symbol correctly.
Now, if you see it differently, though,
then that might mean somebody didn't understand how to draw it.
I've seen that.
And each one of these are supposed to represent a cell. Normally we use this just for generics because electronic power supplies have no cells, right? You understand that? So we call them batteries, but AAAs and AA's and all those are technically not batteries. They are cells. It's just they became known. So if you go way back, they said it was a AA cell, but most people don't understand that. They understand they're car batteries, and they didn't know the difference between a cell and a battery. So now we call all these things batteries, even though technically a 9-volt is a battery. We got one somewhere where we tore it apart. I need to find that, and you can actually see it's got 6 cells in there to get 9 volts. And different chemicals and different makes give you some different volts per cell, right? Understand? So most of our little AA batteries, we say it's 1.5 volts under load. If you measure them unloaded, they should measure about 1.6 volts. So if you pick up a battery, it measures 1.4 volts on your meter, and you throw the sucker away, it's no good at all. So it should measure about 1.57 or something like that unloaded. And we looked up, y'all have all had DC, right? Everybody in here said DC. And series parallel. And then we looked at control circuits. I'm trying to figure out if the circuit up here is working okay. If it's not, we might actually go show y'all the diagram of it. I'll take it and see. Talked about solenoids, we talked about relays, right? Everybody okay with relays? Those are electrically controlled switches, right? And then we looked at symbols. And we call this what type of diagram? Ladder. Pretty obviously why, right? In each individual circuit, we call it what do we call the steps on a ladder? Rungs. So individual circuits on a ladder diagram they're called rungs. So this circuit right here would have 1, 2, 3, 4, 5 rungs. And each one of them consists of either a single element series circuit or multiple element parallel circuit.
I used to say wrong, like R1M.
Rung, like the rung on a ladder. That makes sense. And of course, this is a symbol for a relay coil. You understand that, right? That's the coil of a relay. So that's the electromagnet that actually pulls. And then these guys will have contacts. And you can't really see this, but what we're going to do is we're going to learn that we're going to give your relays are going to have names. So here, if you can't see that, they're calling that M1. And that's just the name that they gave it. The more complex you get into it, the more the name is going to have that. We'll look at some prints that came from U.S. Steel on one of the sections that I used to work out that. And once we get into the rules of actually labeling these things. And then you can't see this right here, but this is a contact. We call this a normally open contact. And it's got the same name, so it means this contact is being controlled by that coil because it's got the same name. That makes sense? Okay. So normally open means if we don't put voltage across the coil, that contact will be open. And as soon as we put voltage across the coil, that contact will close. Are we okay? So these are all outputs. This is the symbol not for a resistor. This is a symbol for a solenoid. So to be a resistor, you got to have probably 4 or 5 of these things. If you only got 2, one up and one down, then this should be the symbol of a solenoid if people draw it correctly, right? Are we okay? So L1, and these are generic terms, and like I said, this gets people in problems in the motor controls, is if we come over here and look at our disconnect over here, the big gray box, it's labeled L1, L2, L3. And those are 208 volts. And then we run it through a transformer. So you'll see the black thing up there, that's the transformer. And what does the transformer do for us?
Step down the power.
Step up, not power.
Okay, watt.
Not watts.
Current.
Yeah, it changes the voltage and the current. We cannot create power. All we can do is take energy and change its form. and the output will always be less than the input. So nothing's 100% efficient, right? You understand? So transformers do not change the power. And the analogy I use, I'm here at this thing, and this is 1,000 watts maybe on all these here. I turn this on. TVA gives me 1,000 watts. Transformers do not change power. If they changed power, then we wouldn't have, the Alabama Power would be have a generator out there that might generate 10 watts, and then they just get all the gain through what? Transformers, right? But transformers do not change power. In fact, power out of the transformer is going to always be a little less than the power in, because there's no such thing as a 100% efficient transformer, right? But we generically call these L1 and L2, which has nothing to do with the power source. This could be DC or it could be AC. PLCs use, programmable logic controllers use a lot of DC. And usually it's a lower voltage. Ours is, so we got one, and we got the 1000, the Micrologic 1000 PLCs that some of y'all are going to be using. This guy is operated off of 24 volt DC, but it switches 120 volts AC. So y'all need to be careful if you get on one of those things. But the things are covered up. You have to deliver to get into them, right? The Micrologic 1100s, we have those down there. These operate off of 24 volts DC, and they switch 24 volts DC. So these are really safe down there. Like I said, you're not going to, as long as you don't open up the covers and get your hands into the 120 volts, you'll be okay. If you're so we call this L1, but when you look in industry, it's probably going to have a certain, they're going to add more to it. So you differentiate between the three-phase power that's being applied before the transformer and then what goes on after the transformer. That makes sense. So yeah, we'll do that in motor controls, and somebody will hook us up over here to L1, L2 on the 208 volt side. And then if we were to apply power on it, it would just burn everything up, right? Y'all know that power varies with the square of the voltage. So if you double the voltage, the power delivered to a circuit, the power delivered to the circuit will go up 4 times. So this is why voltage, and y'all know why, right? Why? Huh? So voltage is equal to, power is equal to V times I. I is equal to V, I is equal to V over R. So we got it in 2 different places, right? You understand? So V is equal to I times R. So what happens if I come over here and double the voltage? No, the resistance side, we're not changing the resistance. We double the voltage to the same circuit. Well, if voltage doubles, the current doubles, and power is equal to V times I. So if both of them doubles, then power is going to vary with the square. If you half the voltage, it's 1 over the square. If you raise the voltage, it's the square, right? You understand? So that means if you got a power, and you can prove it with Ohm's law all day long. So I could come over here and have a 100 ohm resistor, right? Oh, I said 1,000. Let's do it with 100. Y'all get y'all's calculator. We can do it with 1,000. It'll work out no matter what. What's nice about 1,000? What's nice about 1,000? It would be 1 milliamp per volt. So let's start off with the voltage. So let's start off with 12 volts or 10 volts. Let's start off with 10 volts. What would be the power? Well, you could go through all that, but one of our power formulas is power is equal to V squared over R, right? So that would be 10 divided by squared divided by 100. So what would our power be? What's that? Okay, so it's going to be 1 watt, right? Okay, let's double the voltage. So we'll go to 20 volts. So power would be equal to 20 squared over R. No, it won't be 2 watts. It's going to be 4 watts. So that's what most people think. They think if you double the voltage to a circuit, you double the power, but that's not true because current and voltage are directly proportional. So if you raise the voltage, the current goes up, right, to the same load. Let's drop it down to 5 volts. So that's going to be 5 squared over 100. Yeah, so it dropped down in 250 milliwatts. So notice it dropped down by 1/4. So if you go down, it's 1 over how much you go down, right? If you go up, but it's the square. So the power varies with the square. That's why power is so important. I got a call from my mom one day, and she said, "Rich," she says, "my stove won't even boil water anymore." She had an electric stove. And what happened, she lost one of her legs. Instead of putting 220 volts across her heating element, she's only putting 120. And the watts dropped down to 1/4 of what it was supposed to be. And she couldn't even boil water. And that was out on the pole. One of the wires that fed her house actually had come off the line. No idea. Well, I was measuring the voltage instead of having 240 all she had was 120. And I went out, she had a breaker box outside, and I went out there and measured, and it was 120 volts coming in from the wall, from the pole. And I shined the light up there and looked, and sure enough, one of the wires was actually loose. Oh yeah. No, we called the power company at that point. They brought a truck out there. So relationships, right? Voltage drop. Everybody okay on voltage drop, right? We looked at an ideal circuit, but in real life, this is it. We looked at the American wire gauge, and then we looked at what we call the ampacity. This is what the current is rated at on a size conductor on a gauge, but it's at 20 degrees centigrade, right? So what determines the resistance of a conductor? Size, good. Temperature, length, yeah. Those are the 3 main things. Then we looked at the NEC code that they gyrate these things so much. So here it says 14 gauge wire should only be rated at 15 amps if it uses these types of insulation. And power, everybody okay there? What is power? Now it's the rate of doing work, right? Any type of work is the rate of doing something. Shorts, what's the short? An undesirable path. What happened is you've lost control of the current. The current's doing its own thing, right? Shorts, what's going to happen is the total resistance in the circuit will go down, which is going to cause the total current to go up. We have 2 types. We have a short, and then we have a short circuit. Shorts means we have a 0 path of resistance or close to it somewhere within a circuit where it's supposed to have an R. But we don't see these in parallel circuits, but we do see them in series circuits. So you could have a short, but not a short circuit. Right? So if we lose a lot of R, I had a Vega GT when I was in the military, and we pulled a trailer back from California. And when I wired up the trailer lights, I hooked it up directly to one of my lights on my car, on the tail lights. And I didn't take that connection off when I got out to California. And I had a carpet back there. It was a hatchback. And I had a chain back there. And my chain touched the lights and went across that carpet and went to the common of the car. And the chain, so I didn't really have a short almost, because the chain had enough resistance in it where it didn't blow the fuse, but the chain got red hot. Caught that carpet on fire. So I was driving along and my lights dimmed down, and then they came back up. And I was driving along and I saw flashing in my and I turned around and it was on fire. I jumped out of my car and started running away from it. I said, Rich, that's the only car you got. So I run back and popped the hood and threw the carpet out on the side of the road. I need this car, yeah.
You know, experience is a good way to learn. They always look there for it.
Well, I learned a lot then that if you got enough R, you're still not going to blow the fuse. Fuses are not designed most fuses are not designed to handle this. Most fuses are designed to handle short circuits, which gives us a problem sometimes, right? So a short circuit means your source conductor and your return conductor somehow come in contact with each other. So a lot of times we'll overload the wires will get too hot, it causes the insulation is not rated for it. Either the insulation melts, right, understand, or it becomes very brittle. It's not designed to handle it. It becomes real brittle and breaks off real easy. And then you get two wires touching together. People accidentally created shorts. My brother-in-law was doing some rewiring on his house, and he took out a light up there. And he thought that to make the rest of the circuits work, he needed to connect the black and the white wire together up there in his light fixture, because he took the light out. And of course, as soon as he threw power on it, they popped the breaker because he had a short circuit. And I helped him out on that too. So incorrect splicing. We talked about splicing. What's splicing? Well, we bring two wires together, right, or two conductors together. Termination. What's termination?
Yeah.
It's the end point of the conductor. All conductors eventually come to an end. So what's the function of the conductor? Carry current between the source and the load. That's all the conductor's in there for. Defective loads, of course, that happens a lot. Excessive burning off the insulator, and then conductive items falling into a circuit. So that's when you need to tell you to do what. If you got any necklaces or anything on when you're working in this stuff, you need to do what? Take them on. If you got any conductive rings. One of the pictures they showed us in the service was a wrench, and it had a wedding band welded to it, where the guy actually was working on something and hit the ring up against that and just welded.
Didn't show his finger, did it?
No, we did have one where they was talking about taking your rings off, and they showed a finger, and then it showed the tendons coming out of the back of it, where somebody had got it caught on their ring, pulled their whole finger off. Before Christmases and stuff like that, when all the people in the military would take breaks, they would show us these Ohio State films on people that had wrecks, and they'd start pulling people out of the car and all this kind of stuff, and so you'd drive home doing 20 miles an hour. So State Highway Patrol films. So short circuit's not good, right? So technically, according to our math, if we have 0 ohms, the current would go to infinity. But you got to understand that every voltage source has resistance. Now, regulated voltage sources are more dangerous than unregulated voltage sources. The regulated voltage sources, if the voltage tries to drop down, they actually add more energy to try to raise it to go up. Batteries and stuff like that, if you short those out, you can do that. You can take like a double A battery, you can put a piece of wire across it. You got your meter across that, you drop it down and you leave your meter down there, and as soon as you put the wire there, the voltage goes to zero. But what's dropping the voltage? Well, the source is dropping the voltage. The battery itself is dropping the voltage. So this is why if you got your meter out there on your car and you measure 12 volts and you hit that crank, you crank your car, what do you see that voltage do? It's going, well, no, when you're trying to crank your car, the voltage will do what? It'll drop down. Well, what's dropping the voltage? Well, the internal resistance of the battery. Right? You understand that? So all voltage sources have that. Once a regulator gives everything it can, then the actual voltage will drop down. And then, of course, the wires have resistance. So all your voltage is going to be dropped in your voltage source and in the wires. The problem with a regulated voltage source is that when the resistance of the wire starts going up with heat, the regulated voltage source raises the voltage trying to maintain those things. So those things will burn stuff up. We'll try to show y'all that. Where's our big power supply at? Oh my goodness, I gotta find it. We'll burn up a wire for you. That thing's like a 40 amp DC power supply. We can melt some wire with that puppy. But you'll see the wire turn red, and you'll see the voltage on the output of the power supply start going up because it's trying to regulate at whatever voltage. So the current will never go to infinity. Everybody understand that. Mathematically, it looks like it will, but it'll never go because there's always some type of resistance in the circuit. Okay, so this is where when the current flows through the resistance of electric circuit, heat is generated. When the metals are heated, their resistance goes up. When the current goes up, more heat is generated. If something does not stop the current flow, then these guys are going to either melt or cause a fire, right? So we have these devices called OCDDs. You know what that stands for? Overcurrent protection devices. And what's our two main overcurrent protection devices? Circuit breakers and fuse, yeah. Still very popular. Biggest advantage of a fuse, of course, is most of the time they react faster, and of course they're so much cheaper. Go out, if you don't believe me, go down to Lowe's and buy a 10 amp fuse or 15 amp fuse and buy a 15 amp circuit breaker. One of them you'll probably pay $25 for, one of them you'll probably pay $1 for. So the industry is still going to use a lot of fuses. Because why? They're cheap.
I thought circuit breakers would never go out.
No, they'll burn up. They'll go out. They'll eventually go out. So a circuit breaker shouldn't get hot. So one of the things, and it should never drop a voltage. So if you got a circuit breaker that's popping all the time, it might not be because you're overloading the breaker. It might be the breaker's going bad. So when you reset it and you measure the voltage across it, between your neutral and your hot, right? Between the output, it should measure almost 0 volts. If it measures 5-6 volts, you need to go ahead and do what? Replace it. Overcurrent protection devices should drop almost no voltage. And now that'll be on test too. So you should know when you measure across a fuse, it should measure almost 0 volts. It's going to drop some because that's the way it generates heat, right? Understand? And if you measure it with an ohm meter, how much should an overcurrent protection device, if it's not tripped, what should be the resistance of it? Pretty close to 0. Overcurrent protection device. Got that? Fuses, circuit breakers. So this would be a short. This is not a short circuit because I still have a watt. Well, I still have a load. Now what you got to understand is that this could destroy this load. So this load might open because that's shorted, and why? Because it's trying to take care, total current's gonna go up, total power's gonna go up with the square, right? So if these were dropping the same voltage, if they had 100 volts, then that would be 50 volts and 50 volts. This guy's short. Now this guy's going to drop 100 volts and it's going to try to produce 4 times the power, right? You understand that? So a lot of times a short will cause other things to open. So this is a short, this would be a short, this would be a short, and this would be a short circuit. So in series circuits and series parallel circuits, we can have shorts without having short circuits. Of course, the insulator, what's the insulator there for? It allows us to put conductors together, right? You understand that? And it also allows us to handle conductors. Extremely high opposition, but there's no such thing as infinite opposition. So if we teach a class called cable splicing insulation, where we learn that there is current flow through the insulator. We call it volumetric current. But it's so low that we can't measure. But you have a path, right? And insulators don't have infinite resistance. They have extremely high resistance. And if you put voltage across R, you get what? You get I. An open allows no current to flow through the load. No current flows, no work is performed in the section of the circuit in which the open exists. An open circuit prevents current flow through the entire circuit. So this is what your overcurrent protection devices are creating. They're creating open circuits. You create open. We do open circuits on purpose all the time, right? With our off-on switches. So we deliberately create opens. Uses circuit breakers, broken conductors, faulty splices, faulty terminations. Excessive current that causes conductors to melt. So this is an open, this is an open, this is an open, that's an open circuit. See the difference? Okay. So in parallel circuit, every short is a short circuit. Right? But every open is not an open circuit. In a series circuit, every open is an open circuit, right? But every short is not a short circuit. Just about anything you say about a parallel circuit, you reverse it for a series circuit. Right? Almost everything. So we have direct current and alternating current. Direct current flows in one direction through terminals of the voltage source through the circuit, through the load, right? Back to the positive. The voltage never changes polarity. It can change amplitude, but it just never changes polarity. Right? Understand that? Very easy to electronically control. So this is the big advantage of DC, is we can precisely electronically control that. So all your electronic devices operate off of DC. Even if you plug them into a wall, you're going to have some type of power supply that converts it from what? AC over DC. It's real easy to see on your computer. So this is the power supply right here. And it plugs into Alabama Power on one side, and this is DC on this side. DC generators, batteries, thermocouple, solar cells, piezoelectric devices. These guys do it by force. Electronically, AC to DC converters. So that's what these guys are right here. We call these DC power supplies. So these are taking AC and converting them over to DC, right? You got a few of them on your trainer. And then bioelectric. We are bioelectric devices. We create electricity. If you ever watch the metrics, you would understand that, right? So they use us as batteries, right? Then we have AC. And these are just pictures of different devices. Everybody's very familiar with batteries. Solar cells, photovoltaic cells, that's their technical name. Piezoelectric, these guys create electricity when you shock them. So all your lighters most people use, these are piezoelectric devices. Thermocouple, so you've got maybe temperature. AC, alternating current, constantly swaps direction. The voltage source in the AC current constantly swaps polarity, which causes the current to change direction. So here your source and return are constantly what? Changing direction. So technically, we don't have a return conductor and a source conductor because they're constantly swapping direction. Less expensive to generate. So all I have to do to generate AC, let me pause. So the major advantage of that, so to induce a voltage, what do we have to have? We have to have a magnetic field. We have to have motion, and we have to have loops of light. Well, the advantage of AC is it automatically has all that for us. So AC voltage would create a current, right? You understand? So what we can do is we can change the loops, bring these things together. As soon as I find my marker, here we go. So I can have a coils of wire on this side, and then I can have coils of wire on this side, and then I can couple it with metal. And what I'm doing is I'm changing the number of turns, right? You understand? So over here, if I had 200 turns over on this side and I had 100 turns on that side, then I would get 1/2 of the voltage over on the other side. If the current came in this way, then I would double the amount of voltage. And this is all transformers do. Because what does AC give us? AC gives us motion. DC don't give us motion. So transformers won't pass DC. But now we have the ability to change the voltage very, very easy. So we can step the voltage way up for transmission, right? You understand? And when we start getting close to you, we can start doing what? Bringing it down for safety. So that's the advantage of AC. We can step it up and step it down real easy. Don't change power, right? You understand that? A lot of people say that. Major advantage is the voltage can be easily changed with transformers. Also, it induces voltage. It's got motion. So we can take a motor and we can put coils of wire in the center. We call them a rotor. And AC can induce a magnetic field into a rotor. So AC motors are a lot more cheaper than DC motors. DC motors, we have electrical motors always work on the repulsion and retraction of magnetic fields. Well, what's nice about an AC motor is we can induce one of those fields. DC motors, we actually got that thing that's rotating, we got to pass current to that thing. So that means the rotor on the DC motor has to be wound. So DC motors are a lot more expensive per horsepower because they got a lot more copper in them. In DC motors, you're going to have to maintain that transfer thing. Automobile alternators, they generate AC. We use rectifiers, which are made of nothing but our check valves. We call them. We use that converted into DC for power. So your car actually operates off of DC, right? You understand? But you have an alternator. So why is it an alternator? Well, an alternator is just so much cheaper than DC generators. So we have to convert to DC. Mobile generators, I got one of those. I bought one after the big snowstorm back in '93 when the power went out. Power plants, electrical hills generate both DC and AC. So they only put about 10 volts out AC. They use this if they want to stun something. About 850 volts DC when they want to kill people. So that was pretty interesting. Now, that's the only animal I know that generates both AC and DC. DC to AC converters. So what's nice, inverters, is that we can electronically control DC. So we can take DC and electronically convert it back into AC. Which is pretty cool. And then function generators, which are these guys right here. These allows us to generate AC. But we can do it at what frequency we want and what voltage we want. But it's done electronically. We do it at a constant rate, though. The repetition of produced by voltage waveform. We'll talk about this. So we need to understand some terms that you'll run into. This is the way AC is generated. It's generated on a circle.
Oh, cool.
That's cool. And you can actually see the way it's generated. And you can see over here it's forming a right all the time. It forms a right triangle. Yeah, so I could take this anytime. Trying to do this right here. So I could take it any time and I could drop this down and I create a right triangle. And then we could calculate this using what we call trig. We're not going to get into it, but we can take the maximum voltage, we can multiply it. Now this is 360 degrees, right? Understand? We call it electrical degree. So over here I might be at what? I might be at this would be 90, so it might be 135 degrees. So I could take the sine of 135 degrees and I could calculate this length where it's actually over here. So for this reason, whether you understand it or not, this guy is referred to as a sine wave. A sine wave. We spell it with one word. Most people. So if you do it like this, and you got Microsoft Office running, you'll get an error saying it's an illegal term. So this is how it's got its name. And these are symmetrical, guys. So on a sine wave, this guy right here is a mirror image of this guy right here. If we could flip them over and put them on top of each other, you couldn't tell them apart. They're exactly the same. And this is the way power is generated at a sine wave. So I can, what's nice about a meter, what's your meter going to measure for one of these things?
Go up and down.
What's the meter going to measure? So here's some terms. We have, this is called an alternation. Positive alternation, negative alternation. One, we call this a cycle. Everybody okay? So the rate of the cycles, we call that frequency. Alabama Power generates a frequency of, anybody know? 60 cycles per second. So each cycle would last 16.7 milliseconds, 16.6666 milliseconds. So technically, true AC has no sign. We don't say it's minus or we say it's plus. So if you take your digital meter, you could put the red lead on common. It don't make any difference. It's going to measure exactly the same thing because AC has technically has no sign because it's changing direction so fast. So this guy, 60 cycles, is changing directions every 8.3333 milliseconds. It's only at this point right here for a heartbeat. So if I was to come up here and make a measurement, so what are we going to get? You say, well, we're going to get the average. Well, over here, if this is 1 volt, this would be a positive 1 volt. Over here, this would be a minus 1 volt. What's the average of a plus 1 volt and a minus 1 volt? 0. Okay. So if I come up here, so for every positive voltage, we have a negative voltage that cancels this out. And this gets us into trouble. Y'all take a 10-minute break. As I have my meter. And I have it plugged into an outlet here. Got my 2 leads plugged into the outlet. And how many volts does it say I have there? Is there 0 volts there? So I reach my hand in here and I get killed because my meter measures 0. So y'all go out there at home and tell these people to come in. Undoubtedly they can't tell time. I set a timer on my watch. I got my voltmeter. A voltmeter leads plugged into a power outlet. And what's it measuring? It's measuring the average of an AC sine wave. So when you put your meter on DC, it measures averages. It don't measure what's there, it measures averages. So the problem I have, if it's measuring the average, what is the average of a sine wave? The DC average of a sine wave is 0. Because for every positive over here on the positive alternation, you have a negative over there that cancels this out. So I'm going to take my meter, and you see I got my meter on what? DC. I'm going to come over here and just make this little, I'm going to switch it over to AC. And now it's measuring 121 volts. So guys, you can get your butt killed by not knowing, by having your meter on DC and putting it into an AC circuit, because it's going to measure 0. You have this. So what they had to do is they had to come up with a method of calculating, we don't call it an average voltage, the effective voltage. How much AC is going to produce the same amount of work into a resistor. So they came up with a method that we call RMS, which stands for the root of the means of the squares. What that means is we could take, if we could take a lot of measurements, as soon as I get back over to the right one, here we go. So I could take a lot of measurements. Let's stop my PowerPoint. And what we would do is we would square all the measurements, and that would be equally spaced measurements. And we would square them. So this would be 1, and of course 1 squared would be 1, right? But what's a minus 1 squared? Anytime you square a minus number, what do you come up with? You always get a positive. So what they'll do is they'll take a large number equally spaced measurements across the positive alternation and across the negative alternations, and they square them. Then they add them together, mean, which would mean the average. Then they take the average of that, and then they take the square root of the answer, and that gives us what we call the effective voltage. And that's the amount of AC voltage that would produce exactly the same amount of work as the equivalent. So 120 volts RMS would do exactly the same work as 120 volts DC into a resistor. Now, what happens on a sine wave? That value always comes up to be peak voltage, this peak voltage, the peak, times 0.707. Always. So this is what most of your meters do. They use 0.707. But what we have is these only works on sine waves. If you get into non-sinusoidal waves, like generated by a variable speed AC drive or variable frequency AC drive, if you put a regular meter on that, it's not going to measure the effective voltage. So we do have meters out there called true RMS meters. These cost quite a bit of money because they have a microprocessor. They are computers, and they are literally calculating RMS. So these will measure, no matter what the waveform looks like, if it's AC, a true RMS value would give you the effective voltage. If you're using a regular meter, then you might get into some voltages where it's not giving you the accurate voltage because it's using 0.707. That makes sense? So what do you need to buy? Well, if you're an electrician, it's no sense of buying true RMS meters. You're just wasting your money, right? It's like if a lot of people go out and buy these cell phones and they don't use hardly any of the features on them and they pay all this money, right? Because they can tell everybody they got these things. We had a guy, I taught a course in computers, and we had a guy that got really involved with it. He went out and got him a credit at some computer store, and he spent so money and got himself in so much debt that his wife finally divorced him. But he was buying stuff he would never use, right? You understand that? And just to brag about what type of a phone you have. So 0.707 would work great for just about every field y'all have in here. If you work in the industry, 0.707. If you get into places where they have variable frequency AC drives, then if you want to measure the output of those, you get a fairly good idea just for the regular RMS meter, but it's not going to be exactly accurate, right? The variable frequency drives, these guys, they vary their frequency and they don't put out sine waves. They use something called pulse width modulation. They chop it up. So a standard meter won't measure that. So to get, so we call this a peak-to-peak voltage right here. Peak-to-peak, you can imagine, you can peak-to-peak, PPP. So to get 120 volts worth of work, it takes about 340 volts worth of peak-to-peak voltage. Just about 340 volts. But it's no big deal, it's AC. I set it where I want it to be, right, with transformers. And we get the average work. And so if I took 340 and multiplied it by, I take half of that, which would be 170, and then multiply that by 0.707, then that should give us around 120 volts. I think. I'm pulling these numbers off the top of my head.
Yeah.
Yeah. So we're getting a lot more voltage out there to get a lot less work, but we have the ability with AC to do we can step it and get just about any voltage we want. Of course, there are standard voltages, you know. So at your house, you should measure around 120 volts up to, but it's actually plus and minus 10% is actually legal before the power company comes out there and tries to do anything. So if you're above 120, your power bill is going to be a little more because everything's producing, pulling more power, right? If it's less, your power bill might be a little less.
Yeah, where I think mine is like
115 is great.
So that's what yours is.
Well, I don't know. I can't. I think mine's 117. I don't measure mine every day. It changes all the time.
Well, every time I look at it.
Yeah, but odds are, if you can't at night, it might measure a little less. In the summertime, it might measure a little less, right? Because why? Because we got all the line lines.
Well, I thought I was getting cheated. I thought I was supposed to have 120.
Well, 120 is NEC, National Electrical Code, can't say what you get, so they call it the nominal voltage. And so they use 120 and 240 for the nominal voltage. But your odds are you're not going to get those voltages. We're pretty good here. We got 121 volts here. But our power bill is going to be a little more than somebody that's getting 120 volts, right? Because if the voltage goes up, then the power being produced by all of these loads are going to go up just a little bit. So everybody okay? A cycle would be one repetition. Alternation would be positive and negative. Frequency is the rate of the cycle. And the period is what we call the time for the cycle. Which is not very important. Understanding frequency, though, this is the rate that the cycles are changing. And like I said, Alabama Power uses 60 cycles. Does everybody in the world use 60 cycles? No. Europe uses basically, they use 50 cycles. So motors over there run a little slower than they do over here because the AC motors, the speed, one of the main things that sets the speed of an AC motor is what frequency you put higher frequency would be more efficient. Transformers would get smaller because the rate goes faster, right? And that's speed of motion. But our power grid is already set for 60 cycles, and it would just be almost unbelievable what cost it would be to go to a higher frequency. So guys, that's just a little touch. Of course, we have AC. There's a lot to AC. AC, anybody that tells you AC and DC are the same, that is not true. AC, we don't get, right, we get this effective voltage. Like I said, you gotta be extremely careful on your meter in an AC circuit. If you measure 0, you need to verify that it's set on what? AC. Because if you got it on DC, it's gonna measure what? 0. Because that, when you put it on DC, it gives you the average. It don't give you the effective voltage, it gives you that. So questions on that? Do you have any questions or comments or anything? Okay. So when we have PLCs, they're going to give us 3 specifications on a PLC. So on a PLC, we're going to have an inputs, and then we're going to have a control, and then we're going to have an output. So the PLC we're using, one of the PLCs we're using is it's what they call it, AC, DC, AC. And the first one is your input power. This is what you would apply to the PLC to make it come up and work. So it's got a DC power supply within it. DC would be what actually controls it. And then the last one would be what voltage it actually outputs. Make sense? Are we okay? No questions? Okay.